This is our Taylor Polynomials. This is part 2. So in part 1, we learned the basic formula and things, and we did a couple of examples, and now we want to write down the Taylor Polynomial here for this, and they've given us the values. We just need to fill it in. So let's remember what that Taylor Polynomial looks like. So the polynomial here, we're going to do polynomial degree 3. So it's going to be the function, and I'll use g since that's what we're using here. So it's the function value evaluated at 2, because it's centered at 2 here. And then it's the first derivative evaluated at 2 times x minus the place you're centered, plus second derivative evaluated at 2 over 2 factorial x minus 2 squared. And if we were one more, third degree, so we've got to go one more, g triple prime at 2 divided by 3 factorial x minus 2 cubed. And it just keeps going, same pattern, derivative, exponential, power, all the same. So here they've given us all the numbers and everything we need, so all we have to do is fill it in. So our desired polynomial here is g of 2, they tell us right here that g of 2 is 3, so we put 3. G prime at 2 is negative 4, so this is negative 4 times x minus 2. If you want to, you could just write minus 4 times x minus 2, plus g double prime of 2 is 7, so 7 over 2 factorial x minus 2 squared, plus g triple prime at 2 is negative 5, so I'll just write minus 5 over 3 factorial x minus 2 cubed. So really follows patterns, really pay attention to that, and it's really easy to do. Okay, so it really is very easy, and it will make more sense the more and more we do these, and especially when we get to series, how it can, when it converges, and how it, when it actually equals things and that kind of stuff. So just go ahead and be practicing right now. So here we want to do a third degree Taylor approximation near 0 for e to the x. And then we're going to use that answer to find the limit, which basically means we're going to substitute the polynomial we find in place of e to the x. Because remember, a limit is just what is that thing approaching anyway. So that's what we're going to look at. All right, so third degree polynomial. So f of x is e to the x. So then we need to find f prime, which is, oh, e to the x. F double prime, e to the x. F triple prime, e to the x. So this is a pretty easy one because they're all e to the x. Then what we have to do is we're doing it near 0, so we're going to plug in 0. So e to the 0 is 1. So f prime of 0 is going to be e to the 0, which is 1, and f double prime of 0 is 1, and so on. So this one's pretty simple. All your coefficients are 1s there. So what that means is that e to the x is approximately equal to the function value at 0, which is 1, plus the function value at 0, or the derivative at 0, which is also 1, times x minus 0. So that gives me x, plus the second derivative evaluated at 0, which again is 1, they're all 1, times x squared, and then that's all over 2 factorial. Then when you get to the third derivative, your coefficient is 1 again, and it's going to be x cubed over 3 factorial. So you can see the pattern very quick on that one. What that's going to equal if you wanted to go further and further and further. But right now that's all we want. We just want the third degree one. So we know that e to the x is approximately equal to this. So if we're doing the limit as x goes to 0 of e to the x minus 1 over 2x, well, that's approximately the same thing as substituting for e to the x this polynomial that we just found. And then minus 1. So this polynomial, I'll write over it in red, all of this was just your e to the x. So that was e to the x. So we replaced it. And then you're going to have minus 1 all over 2x. And then we need to do this limit. Well, we can see here that you have a 1 minus a 1, so that won't be there anymore. And then basically your when you're doing your limit here, notice that every term has an x in it now that the 1's are gone. So that means this is the same as the limit as x goes to 0 of 1 plus x over 2 factorial plus x squared over 3 factorial, all of that divided by 2, because I simply took an x out of everybody. All of them had an x, so I took one x out. Now when I do that limit, as x goes to 0, well, if x is going to 0, then that goes to 0, that goes to 0. So I'm left with a half. So my answer to this is 1/2. Well, if we do the actual limit, this was the supposed approximate limit because I replaced e to the x. So let's do the actual limit. Okay, so we have a process and a way to do this. Okay, so the first thing we do is plug in 0. So we plug in 0 for e to the x. So we'll get e to the 0, which is 1. 1 minus 1 is 0. Put a 0 here, 0 over 0. So we use L'Hopital's rule, and we do the derivative on the top, which is e to the x, derivative on the bottom, which is 2. Now let x go to 0, and we get 1 over 2. And that's exactly the same answer. Now, it shouldn't be too surprising because remember that a limit is purpose is what happens as you get really close to 0, not necessarily equal 0. So this thing was a very good approximator for e to the x, but especially because I was looking for a limit. Where is it going if we kept going? All right, so let's do our last couple of examples here. So example 7, we're saying, say we have this polynomial and it's a second degree polynomial. What can we say about what a, b, and c must look like if this is f over here? Okay, so this graph over here is f. And we know that we have some second degree polynomial, and we want to know just about the signs of a, b, and c in this right here. Okay, so in this second degree polynomial. So let's figure out what that would look like. Well, if I were making that polynomial, remember that a would have come from being just the value of the function evaluated at 0, because we're doing it about 0, would have been the evaluation of the function at 0. Well, the function value at 0, we can see it right here on the graph. There's a function value at 0, and it is certainly positive. Okay, and that's all we said. What are the signs? So we can see that the first derivative, or a, has to be positive. Then we can do the same thing for b. B is your coefficient here, so it would be the first derivative evaluated at 0 for your coefficient divided by 1 factorial, which is just your first derivative at 0. Well, the first derivative means that we're looking for what is the slope right here of a tangent line. So if I were to draw a tangent line right here, what sign would the slope have? Well, it would be positive. So b is positive. C in the problem is your second derivative, because it's the second derivative at 0 divided by 2 factorial. That's what you would put if you were writing this out. Well, the second derivative tells us about concavity. Well, at 0, this thing is clearly concave down. So if we look at it, we can see it's concave down. So therefore, this must be negative, because if you have concave down, you have to have c less than 0. Okay, so there we go. So a is positive, b is positive, c is negative. And that's kind of how this is all relating to each other. All right, so then let's do this last example. And this example says sometimes we can actually before this tells us sometimes we can actually get new polynomials without starting from scratch and doing them all. So one thing you probably want to write kind of down towards the bottom of the page, there are a few Maclaurin polynomials that you're going to end up needing to memorize. One of them is sine x, and we've already looked at it. We looked at the sine x. It was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. If I keep going, it's minus x to the 7th over 7 factorial. Think about what would be next. If we were going to keep going, that would be x to the 9th over 9 factorial, and it just continues like that and has that pattern. Now, I'm saying dot, dot, dot. If it's a polynomial, it's going to stop. We're going to talk about series in the next section, and we're going to put dot, dot, dot. It's going to go on forever. But you can see the idea here, and I can't put equals. I got to put approximate here because I am stopping it. So there's an example of a polynomial that represents sine. Something to notice about that is that sine, if you remember, is an odd function. And you'll notice here all your powers are odd. This polynomial is also odd. Now, let's talk about cosine x then. Well, we didn't do cosine x, but guess what? Cosine is the derivative of sine. So all we have to do is take the derivative of each of these terms, and we get the Maclaurin polynomial for sine. So because we notice that the derivative of sine is going to equal cosine, we're just going to take the derivative of all of the terms over here. So the derivative of x is 1. This next derivative, you're going to get a 3 in front because you're going to put 3 here, and then you're going to lower the power by 1. Well, that 3 that goes here is going to cancel with the 3 there, and you're going to end up with x squared over 2 factorial. Plus, do the same thing. That 5 comes in front, cancels with the 5 on the bottom. You get x to the 4th over 4 factorial. So you can see the pattern now. Don't even have to keep doing that. The pattern is clear. And if you kept going and going and going, you can see what the pattern is. Now, again, not too surprising. Cosine is an even function, and you got all even powers. Another one is e to the x, and we already did that one today. It was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5 over 5 factorial, and so on, as many terms as you need. So those are going to be some of the ones that we're going to need to learn, especially when they're series. So let's use that to generate these new ones without having to start from the beginning. So if I want to do sine of 2x, all I'm going to do is take this series right here, and I'm going to put 2x everywhere I see an x, and that's it. So sine of 2x is approximately equal to 2x minus 2x cubed over 3 factorial plus 2x to the 5th over 5 factorial, and it said not 4 non-zero terms, so we'll go one more, 2x to the 7th over 7 factorial. Very common to tell you to name 4 non-zero terms. Now, I could stop there. I would just leave it, or you could go ahead and if you wanted to, you could multiply the numbers out and simplify it and everything, but I would just leave it, and there you go. There's your 4 terms. So let's look at the next one. We have x times cosine x. Well, you have cosine x written here below. All I'm doing is putting an x in front of it. So that's all you're going to do. You're going to take this formula right down here, and all you're going to do is multiply everybody by x. So 1 times x is x, minus, instead of x squared, it'll be x cubed. Instead of x to the 4th, it's x to the 5th. And instead of x to the 6th, it'll be x to the 7th. And that's how easy it is. That's all you're doing. So we can do all kinds of changes to make that work. So let's go ahead and go on the next page to do 4e to the x squared. So here we have the formula for e to the x, and let me go ahead and write that one down again. That one was the easy one. super easy. All you're getting is just the power over the factorial of the same power. So let's first just do e to the x squared. So that means everywhere you see x, you replace it with x squared. So we'll have 1 plus, and instead of x, you'll have x squared. And here you'll have x squared squared, so that's x to the 4th. And then you'll have x squared to the 3rd, which would be x to the 6th over 3 factorial, and there's your first 4 non-zero terms. But it was 4 times that. Well, guess what? Put a 4 here. All you have to do is put a 4 there, and there you go. So technically, we would put 4 plus 4x squared plus 4x to the 4th over 2 factorial plus 4x to the 6th over 6 factorial, and there you go. So once you know some of these, you can use combinations of them in order to generate another Maclaurin polynomial. And like I said, it will make a lot more sense once we get into series and things, why we're doing this and what we're using them to represent. So right now, just practice the format and watching for the patterns. That's the main thing, and starting to kind of learn them a little bit.